In this section of the chem activity number 14, we will explore the various parameters that affect an ideal gas and see their interrelationship. Specifically, we'll change the pressure, we'll change the temperature, and we'll change the amount to see how those changes affect the volume of a gas. The first relationship that we will look at is the relationship between volume and pressure. This is often referred to as Boyles Law, after a gentleman scientist from the mid-1600s. And although Robert Boyle is known for this law, I think more importantly, he's known as being among the first scientists to actually think about experimental design. That is, to change a variable and then see the effect of changing that variable. And so he made huge contributions to our understanding of the scientific process. Before we look at the notes here, I'd like to turn to a simulation. In this simulation, you see a series of gas particles. You can see that they're in constant random motion. The gas particles in this case are meant to be particles of hydrogen. Right now the pressure is set at 1 atmosphere, the volume 22.4 liters, and the temperature 273 Kelvin. Now the idea is that we are slowly increasing the pressure by decreasing the volume. And we're now up to around 2 atmospheres. And perhaps you've noticed that the volume actually has halved. Or another way of thinking about it is we have the volume from 22.4 liters now down to 11.2 liters. Now there's a relationship between volume and pressure. If the pressure doubles, the volume halves. If you think about how the particles are colliding with the walls of the container, which is indeed what causes pressure, in this smaller volume, you can see the particles have less of a distance to travel, and therefore they're going to collide with the walls of the container more frequently, and therefore exert a greater pressure. So actually, I think I want to come back to this situation of the greater pressure. So right about here, one of the things I'd like you to notice is that the temperature is not different. So I'm going to keep coming back so you can take a look at this. The temperature hasn't changed, but what has changed is that the particles are now colliding with the walls of the container more frequently because there's a smaller volume. So now we increase the volume or decrease the pressure, and you can see we're back to the 22.4 liters and 1 atmosphere pressure. You may also remember that not all the particles are moving at the same speed, although they would all have the same average kinetic energy. Now that you've seen the simulation, perhaps you can take note and understand the general conclusion here. The volume of a sample of gas is inversely proportional to pressure if the temperature is held constant. And of course, we're also holding constant the amount of gas that's present. So it's the idea that there are 4 parameters, but you change only one and you see the effect on another. You keep 2 of the other parameters constant. So in my little drawing here, we have condition 1 going to condition 2. And this replicates what we saw in the simulation, although the numbers are a bit different. So we're going to keep the amount of gas constant, in this case 6 moles and 6 moles. So imagine that each of those little balls represents a whole mole of gas. We'll keep the temperature constant at 298 Kelvin, but we'll have the volume. Now having the volume means that the particles have a smaller distance to travel. So initially, the gas was at 1 bar. I think we can predict what the new pressure will be, especially given that it's inversely proportional. And when we say proportional, this means that if you change one factor, the other factor will change by the same degree. So half the volume will mean that the pressure indeed should double. So we would expect 2 bar here. And at the submicroscopic level, we understand that with the smaller volume, the particles have a less distance to travel. Therefore, they're going to collide with the walls of the container more frequently. Now, it's also important that you can think about this relationship by an equation. So I'm showing it to you here. We say that volume is inversely proportional to the pressure, but it's not that volume is equal to the inverse of the pressure. It's equal to a constant times the inverse of a pressure. Now, you'll never need to calculate this constant, which I'm referring to as KB, the B standing for Boyle. Rather, we'll see how we can combine all the different constants for the relationships that we're going to discuss into one constant that we'll refer to as the ideal gas law constant. It's important that you understand there has to be a constant here, because we can't say that volume is equal to pressure or 1 over pressure. Volume has units of mils and liters and centimeters cubed. Pressure has units in atmospheres. They're different concepts, if you will. Now we can draw a graph to show this relationship, and we'll put the volume always in the y-axis. And one of the ways we can represent this is we'll put pressure here, and we'll understand that as the pressure increases, we expect the volume to decrease proportionately. If we start at a very low pressure, which would correspond to a high volume, and increase the pressure, we'd expect a relationship something like this. So it's kind of a curved relationship. However, if down here we plot 1 over pressure, a different sort of relationship will be seen, in the sense that we would expect that volume is, in a sense, directly proportional to 1 over the pressure. And the slope of this line would equal KB. Before we move on from this slide, once again, I want to remind you that we're exploring the relationship of volume and pressure, but this is at constant amount and temperature. This relationship only holds true if you keep the amount and temperature constant. If they were changed, well, then we could account for this, but you wouldn't see this inversely proportional relationship. So now let's explore the relationship of volume to the temperature. And to do this, I'd like to return to our simulation. In this next part of the simulation, we're going to start at 273 Kelvin, and we're going to increase the temperature. All along, we're going to keep the pressure constant. So the idea is that we're always going to change one variable and see its effect on the volume. So as we increase the temperature, you can see that the volume is increasing. Again, the pressure is remaining constant. Now I'm going to pause the video for a second so the particles are no longer moving, but I just want to talk you through the effect here a bit. So remember that as the temperature is increasing, the average kinetic energy of the particles also increase. And if nothing else happened, that is, if the volume remained constant, the fact that the particles are moving faster, they would collide with the walls of the container more frequently. And indeed, the pressure should go up. But because we're keeping the pressure constant, the only way that that pressure could be kept constant is if the volume increases. So although the particles are moving more quickly, they have a longer distance to travel before they hit the walls of the container. And indeed, as the temperature increases, you can see that the volume increases. And we will find out that this is proportional. So if the temperature in Kelvin were to double, the volume in turn would also double. You can see definitely at this higher temperature, the particles are moving much more rapidly. And again, though, not all the particles are moving at the same speed. Now that we've seen the simulation, understand that the relationship between volume and temperature is referred to as Charles' Law. So Charles was a Frenchman. He was a scientist towards the end of the 1700s, and he was among the first to look at using balloons for elevation. And in those days, there were two kinds of balloons. One was, in a sense, heating air such that then what's contained inside the balloon would have less density than the surrounding air, and the balloon would rise. But Charles' approach was to actually fill a balloon with a gas that was less dense than air, and that gas happened to be hydrogen gas. And so I'll tell you a little bit more about his adventures in using these gas-filled balloons for travel along the countryside of France. The statement of Charles' Law is the volume of a gas is directly proportional to the temperature if the pressure and the number of moles, or the amount, is held constant. So again, we're only focusing on the relationship of volume and temperature at constant amount and pressure. Now, as simulated in the animation, the volume is directly proportional to the temperature. But it's very important that you understand that this must be temperature in units of kelvins. This directly proportional relationship does not apply if the temperature is in degrees Celsius. So if we take a look at our condition 1 versus condition 2, we have the same amount, 6 moles. We have the same pressure, 1 bar. What we're going to do is see what temperature is required to change the volume from 20 mils to 40 mils. And as you might imagine, if the volume is doubling, well, then the temperature indeed will double. But note that this is not a doubling in Celsius, but rather in Kelvin. So therefore, the new temperature needs to be 596 Kelvin. And again, the reason why this happens is in order to keep the pressure constant, if we have a higher temperature where particles have a greater average kinetic energy and are moving faster, we need a bigger volume. And as it turns out, these are directly proportional. So once again, if I put volume in the y-axis and I'll put temperature in the x-axis, and as the temperature increases, the volume will increase proportionally. And of course, the slope of this line would equal Kc. You'll never calculate this Kc, but understand that it represents that proportional constant between volume and temperature. And of course, the C here stands for Charles. In the next simulation, you'll see what happens when we change the amount of gas in a container, but we'll keep the pressure constant as well as the temperature constant. In this next part of the simulation, we're going to change the amount of particles while keeping the pressure constant. So now we're decreasing the amount from 1 mole down to 0.9, down to 0.8. It's like there's a leak. And again, we're keeping the pressure constant. So again, I'm going to stop this video for a second. We've halved the amount of particles, yet we want the pressure to stay the same. The only way we can have the same pressure with half the number of particles is if the volume itself is smaller. With fewer particles, smaller volume, they'll still be colliding with the walls of the container at the same frequency. And you may notice we have the number of particles, and indeed the volume is halved. So again, the relationship here is that they are directly proportional. The relationship simulated in the animation is often referred to as Avogadro's hypothesis. Now, it's worth reminding you that we call the number 6.022 times 10 to the 23 Avogadro's number. But recall that this number was not conceived of really until the 1860s and actually wasn't measured until around 1905. So Avogadro had no idea about this number. Rather, he proposed that samples of different gases, which contain the same number of molecules, would occupy the same volume. So actually, he was getting at a way of counting the number of molecules that are present. If you compare two balloons filled with the same or with different gases, and both balloons are at the same temperature and pressure, and assuming the same elasticity of the balloon, and they have the same volume, well, then you can predict that they would have the same number of molecules. If one gas had twice the volume as another, but still at the same temperature and pressure, we could say it had twice the number of particles. So this points to one of the reasons why the scientists decided to name the 6.022 times 10 to the 23 after Avogadro, is he was the first to really get at the idea of counting the number of particles and associating with, in this case, a volume of a gas. So we saw in the simulation that if we added more particles to a container, yet we keep the pressure constant and the temperature constant, well, indeed, the volume has to increase. And so if we started with 6 moles of gas particles and we doubled the number of gas particles, we would indeed expect the volume to double as well. And hopefully this makes sense to you, especially if we're trying to keep the pressure constant. If you add more gas particles, Certainly there'd be more collisions with the walls of the container, and the only way that the pressure could be held constant is if the volume also increases and increased by the same amount. So if we make a plot of volume versus amount, and once again we're going to see that this relationship is directly proportional. And as you might imagine, the slope of this line would equal Ka. Again, you're never going to calculate Ka, and of course the A refers to Avogadro's number.